As we'll continue to discuss in this chapter as we explore entropy in more detail, entropy has to do with the second law of thermodynamics, and entropy is always increasing. So we'll talk about the entropy of the universe in another couple of problems. But again, thinking about entropy, think of the term disorder, think about more molecules moving more, and favorable processes either make more molecules or increase movement. And as we already mentioned, entropy has a temperature dependence and so is affected by physical state and thus phase changes. In our previous sample problem 20.1, we predicted kind of entropy looking at different molecules. In our next problem here, we're going to calculate entropy using Appendix B, which are standard thermodynamic values, and an equation looks very similar to what we've already seen in Gen Chem 1 in Chapter 6 when we applied this to enthalpy. So again, we used Appendix B in Chapter 6, and we're going to use it again. I'm going to just show you a couple of examples here, and then I won't flip back and forth between Appendix B, but I'll just show you how to use it. For our first problem that we're going to work through, here's just a couple of molecules that we'll see. We're going to be talking about the combustion of propane gas here. So here's propane gas, and one of the products is carbon dioxide gas. So as you can see, there's different substances or ions that are in this table, and then there's three columns here having to do with the enthalpy of formation, the free energy of formation, or the entropy. Notice too that the units are different. Enthalpy and free energy are kilojoules per mole, and then entropy is joules per mole Kelvin. Again, the Kelvin there to remind us that entropy has a temperature dependence, and the units are given in joules per mole, not kilojoules per mole. So if we ever have to combine these terms, we'll have to make sure that we consider that so that we know we have the correct units for adding together. So we'll use values from Appendix B. Again, I'm not going to flip back and forth with this because it's going to get a little cumbersome, but you want to make sure that you grab the right phase. So for example, carbon dioxide here has gaseous carbon dioxide, has aqueous carbon dioxide. So we want to make sure that we're grabbing the right substance for the problem we're working on. So again, we're going to use this equation in our next problem to calculate the entropy for a reaction. Okay, so the reaction that we're looking at is propane gas, the combustion of it to generate carbon dioxide and water. So the first thing that this problem asks us to do is to predict the sign of delta S of reaction. And again, we can do this when we're looking at chemical reactions largely by counting the number of gas moles that we have between the reactant side and the product side. So if we do this, we can see that we have 1 plus 5. We have 6 moles of gas as reactants. And don't count up to 7 here because water here is not gaseous water. It's liquid water. And that's going to become important when we look it up on Appendix B, that we have to make sure we look up the correct phase here. So liquid water doesn't add into our count here. So we really only have 3 moles of gas as products. So the delta here is that there are 3 more moles of gas as reactants. So we go from 6 moles to 3 moles. We've in reality decreased the number of moles of gas through this chemical reaction. And so in this case, entropy would be predicted to be unfavorable. And remember, for unfavorable entropy, that's predicting a negative sign for that. So what we're going to do now is we're going to use our Appendix B. We're actually going to go through and calculate this. So what I like to do, and I'm just going to rewrite this equation down here so you can see this, is I like to write my thermodynamic terms right under the equation. So I make sure that I can see my coefficients that are there, and I match up the correct terms with the correct values. So I'm going to do delta S. So we need to look up our S values from our appendix. And note that the units are going to be joules per mole Kelvin. So I'm just going to write down what these values are, keeping in mind that I had to look them up from my Appendix B here, making sure to look up the correct substance and the correct phase, and making sure that I'm looking in the entropy column here, not in the free energy or the enthalpy column. All right, so here are the values that we have. 269.9, 205.0, 213.7, and then 69.9. I'm not writing the units here because I have my units represented over here. Now, the equation, again, that we're going to use to calculate the entropy of the reaction is that the entropy of the reaction is equal to, oops, this is supposed to be a sum here, a sum, the summation of the entropy of the products, and again, they're going to be scaled by the coefficients from the reaction, and then we're going to subtract any of the entropy of the reactants, and again, those are each going to be scaled by coefficients in our chemical reaction. So let's see if that makes sense here. So if we want to figure out delta S of reaction, again, it's going to be products minus reactants, and I have to consider the coefficients that I have here. So I'm going to use big brackets to kind of sum up the product terms and then the reactant terms, and then I'm going to use parentheses to kind of separate anytime I have to scale one of these values. So I have 3 moles of carbon dioxide, so I'm going to have a 3 then by 213.7, and I'm going to keep my units off here just to keep my writing simple, but we're going to remember that our units when we multiply number of moles are going to be joules per Kelvin. So when we have 3 moles times units of joule per mole Kelvin, mole will cancel and I'll be left with units of joules per Kelvin. All right, so 3 times this value plus 4 times 69.9, and that completes the summation of all of my product terms. Now I'm going to subtract the summation in any of my reactants. So it's 269.9, and there's only one of those, plus 5 times 205.0. Again, brackets to kind of keep my products and reactants separate, and then parentheses so that I can scale each of my entropy terms by the number of moles that are present in my balanced chemical equation. Go through all of this math and you get a value of negative 374 joules per Kelvin. We had already predicted that it was going to be negative based on the counting the number of moles of gas, and indeed that is the case for what we see here, that the entropy is unfavorable.